Hi, welcome everyone. Today we're going to be focusing on hypothesis testing, more specifically the z-test for proportions, t-test for mean, and then chi-square test for variance. These are all things that we've covered. I'm going to be going over basically a tutorial and practice problems that I will have posted for you soon. So you'll have access to that. Follow along with the video. Try to do the calculations. If you are getting the correct calculations, you are on the right step. And remember, order of operations is something that we really try to hammer in, so make sure you're on top of that. So we're going to first start with a t-test. So with a t-test, the key word is average or means. If you see average or means, you know it's going to be a t-test. That's your first step. Now, from there, I would have to give you a problem and give you different types of situations as well as statistics in order to help you answer this question. So I'm going to be reading off my prompt, but you will have access to these same prompts very soon. So for a t-test, we're going to say a sample of 25 students has an average score of 72 on a math exam with a sample standard deviation of 8. The instructor claims that the average score is less than 75. Test this claim at a significance level of 0.05. So a couple things that we need to dissect here. The first thing I tell you is a sample of 25 students, and I say there's an average score. So the average score, that should give away that, hey, I'm working with a t-test. So the average score of 72 on a math exam. And then I give you the sample standard deviation of 8. And then the instructor claims that the average score is less than 75. So the less than 75, that is going to be our alternative hypothesis. That's what we're trying to test. We're going to test it at the significance level of 0.05, which you all know. Significance level is alpha. So I'm going to write down some of the important stuff just so you have access to it. So we said n equals 25. Our mu is going to be 75. Our x bar, in this case in our sample, is 72, and our alpha is 0.05. And then I also gave you your standard deviation of 8. So these are all the important statistics that you're going to need for this problem. So in the question itself, I ask you the instructor claims that the average score is less than 75, and we want to test this claim. So what I gave you is not the null, but the alternative. Now from the alternative, we know the symbol that we're going to use is mu. The reason why it's mu is that's the parameter for populations. So mu is going to be less than 75. So it's going to be less than 75. And you know if your alternative is mu is less than 75, the null is going to be mu is equal to 75. So these two values will always be the same. These two symbols will always be the same, regardless of what test that we do. The only thing different is going to be the inequality right there. All right, so the next step for a t-test, if you look at your steps, is going to be finding the t-stat, or our evidence. The evidence is what's going to help us make the distinction, whether we reject or fail to reject. And the whole point of a hypothesis test is to provide some type of validity and strength to whatever argument you're trying to make. So in this case, our argument is we think that the average is going to be less than 75. So that's the claim that we're trying to test to prove it to be true, to prove it to have enough evidence to support the claim or not enough evidence. So our t-stat formula is going to be x bar minus mu over the standard deviation divided by the square root of n. So you have this formula in your notes. X bar, you notice, is given to us right here. Our mu here comes from the null hypothesis. So if you look at the mu, we know it is going to be 75. That is what is in our null hypothesis. I give you all the other values, you would plug this in, right? So we're just going to do it right here on the side. So our t-stat, we're going to plug in 72 minus 75 divided by 8 over the square root of 25. If I do all this math, when you put it into your calculator, you should get a negative value. The negative value should be where is it? Let's do 88. So you should get negative 1.88. If you're getting negative 1.875, that's also totally fine, but we're going to round it to 2 decimal places. So negative 1.88. All right, so that's part of the problem right there, is finding the t-stat. This is our evidence. Now we want to compare this to our t critical value. So I'm going to erase this really quickly. So I'm just going to put the t-stat right down here somewhere. So your t-stat is negative 1.88. Now we want to find the t critical value. So our t critical value, we know it's going to be t of alpha, comma, n minus 1. Now, because this is a left-tailed test, our t critical value has to be negative. So because this is less than, your t critical value is going to be negative. So what that looks like is in our distribution, anything on the left-hand side, or in this region right here, is going to be reject the null. Anything to the right-hand side of this is going to be FTR, which stands for fail to reject the null. Now to find the critical value, we use this formula. So the alpha for this problem, if we look right here, is t of 0.05, comma 25 minus 1. If I look this up in my table, what I should find is negative 1.711. So that's what is going here. So anything on the left-hand side, or within this shaded region, is going to be reject. Anything to the right-hand side is going to be fail to reject. So now, our decision. So because negative 1.88 is in the rejection region, we say we reject the null, and there is enough evidence to support that the mean exam score is less than 75. So again, we're providing some validity to our initial claim. So again, negative 1.88, it's in the rejection region. We reject the null, conclude there's enough evidence to support the alternative, which is this right here. Now, the next part of this would be, I ask you for a confidence interval. So a confidence interval. So for this, we're going to assume that you're going to have a 95% confidence interval. 95% confidence interval. So 95% CI stands for confidence interval. The formula for this is x bar plus or minus the t of alpha divided by 2, comma n minus 1. And we multiply all that by the standard deviation and the square root of n. So this is already given to you. You have all this information. We find this portion on our t-table. So this portion is found on our t-table. So if I were to plug all this stuff in, what I'm going to get, I'm going to do it right up here. So we're going to plug in our x bar, which is 72, plus or minus. And when we find our t of alpha divided by 2, so our alpha in this problem would be 5% because I'm giving you 95%. If this was 90%, alpha would be 10%. So it's alpha divided by 2, so we're going to try to find t of 0.025, comma 25 minus 1, which is 24. And then you plug in the rest of the values that you already know, 8 divided by the square root of 25. Now after you do all this math, you're going to get your LCO and your UCO. So with your LCO, the value that you should get is 68.70, and then the next one should be 75.30. Now if you're struggling finding this, it should be 2.064. So whatever this value is, you're going to look it up on the table, add it in here, and then go through the calculations. But this would be the LCO and the UCO. So you could say the 95% confidence interval for the average exam score is in between 68.70 and 75.30. So that's how you would do a t-test. and this is going to be a left tail t-test was what we did. And on top of that, this is a 95% confidence interval. So we're going to do a couple more just so you get more familiar and more comfortable with all this information. All right, so the next question we're going to be doing is going to be a t-test again. So I'm going to read off the question, and you're going to have access to these questions soon. So a company claims that the average weight of its product is more than 200 grams. A sample of 30 products has an average weight of 198 grams with a standard deviation of 5 grams. Test this claim at a significance level of 0.01 or 1%. So reading the question one more time, a company claims that the average weight of its product is more than 200 grams. When you see average, you should think t-test. And it says more than 200 grams. That first sentence is giving you your alternative hypothesis. So we're going to start with that right up here. The alternative is mu is greater than 200 grams, meaning our null is going to be mu is equal to 200 grams. Now, I give you a sample of 30. I give you the sample mean of 198, standard deviation of 5, and then alpha is 0.01. So all important things that you need. We're going to go through the same steps. You're going to find your t-stat. So you should know the formula that I'm referencing now. So it's going to be x bar 198 minus 200. We divide that by our standard deviation, which is 5, and then the square root of 30. If I do all this math, I should get negative 2.19. So negative 2.19 is what you should be getting. Now our t-critical value. This is a right tail test, so our t-critical value is going to be positive. So what we want to find is 0.01 comma 30 minus 1. So if I were to look this up on my table, you would go to your t table, you go to the column that has t of 0.01, you go all the way down to 29, and you should get 2.462. All right, now you'll notice a couple things here. So if we draw our distribution, this is a right tail test because it is greater than. Because it's a right tail test, anything greater than our t critical value is going to be a rejection region. So anything greater than this, reject. Anything on the other side would be fail to reject. So 2.462. Anything greater than that value, we're going to reject. We notice that our value is negative. So negative 2.19 does not fall in the rejection region. So our decision in this case is going to be fail to reject the null. There's not enough evidence to support the claim that the average weight of the product is more than 200 grams. So that's how you would make your decision with a right tail test. The next step would be a 95% confidence interval. So again, we've looked at the formula before. I trust that you can plug this into your formula from our previous problem. It's the same exact thing again, right? So it's the x bar, which in this case is 198. It's going to be plus or minus t of alpha. So alpha is 1% divided by 2. Oh, I'm sorry. So I made a mistake a lot of students make. So if I ask you for a 95% confidence interval, my alpha is now 0.05. It's not 0.01. So that's a common mistake, and then students will use what I was about to do, is going to use that 0.01, which would be incorrect. So it's 0.05. So t of 0.05 divided by 2, comma 30 minus 1. And you plug in everything else, 5 divided by the square root of 30. So the t critical value here, I find on my t table. So I'm just going to double check my work really quickly. So it should be 2.045. If I plug all this in, my LCL is going to be 196.13 my UCL is going to be 199.87. So that is 8. So with 95% confidence, the average grams is in between 196 grams and 199.87 grams, something along those lines. So you should be able to get to that conclusion using this information. The next problem we're going to do is going to be another t-test. Again, I just want to give you exposure to all three types. So the next one, we've done a right tail test, we've done a right tail, a left tail. The next one, you can probably guess, is going to be a two-tail test. So the next one, we have a two-tail test. So now we're going to say we have a manufacturer claims that the lifespan of tires is 52,000 miles. And we have an independent group that found that this amount is different than what is claimed. A sample of 16 tires has an average lifespan of 50,000 miles with a standard deviation of 2,500 miles. Test is claimed at the significance level of 0.05 or 5%. So the mu, what we're going to assume to be true, is 52,000 miles. That's what's assumed to be true. What this independent group is trying to test is it's not 52,000 miles because it says different than what is claimed. That's what we're trying to test. So the n in this case is going to be 16. The x bar in this case is going to be, the x bar is going to be 50,000. Standard deviation is 2,500. And alpha is 0.05. All right, so in this space, we're still finding our t-stat. So it's x bar, which is 50,000, minus 52,000, divided by the 2,500 over the square root of 16. If I do all of this math right now, what I'm gonna get is negative 3.2. So negative 3.2 is my test statistic. So what we want to find now is our t critical value. So t critical value, an important thing with a two-tailed test, so when it's different than, you have to divide alpha by 2, and then comma n minus 1. So this t critical value is going to be positive, and it's going to be negative. So if I were to draw my distribution, you're going to have two rejection regions now. So the reason why we do alpha divided by 2, this area right here is alpha divided by 2, and this area right here is alpha divided by 2. If we add both of them together, it's going to equal alpha. So in this case, if we do alpha divided by 2, this shaded region should be 0.25 of the curve, and this shaded region should be 0.025 of the curve as well. So it's going to be 5%, which is what we have here. So my t critical value in this case, what I'm going to look up is t of 0.025, comma 15, right? Yeah. So it's going to be 15. So if I go to my table, t of 0.25, go down to 15, what I'll see is plus or minus 2.131. So if it's negative 2.131, and positive 2.131. Anything in the shaded regions, we are going to reject. Anything in the unshaded regions, we are going to fail to reject. So in this case, negative 3.2, does it fall in the rejection region? The answer is yes, it does. So in this case, our decision is we reject the null, conclude there's enough evidence to support that the average lifespan of a tire is not 52,000 miles. So we have enough information and evidence to support whatever our claim is going to be. All right. So the next one is going to be your confidence interval. So 95% confidence interval, x bar is 50,000 plus or minus t of alpha divided by 2. Again, we're asking for 95% confidence. 16 minus 1. and then 2500 divided by the square root of 16. Now this value right here, have we found this before? The answer should be yes. It's what we have down here. Same exact thing. So you would plug in 2.131. And again, for every single test that we're doing in this video is going to be 95% confidence. So 95% confidence. So the reason why it's the same value here is our alpha is 5%, and the alpha here would also be 5%. We just divided by 2. So our LCL for this problem is going to be 48668, and if you're in the ballpark, you're good. 51331. Somewhere in between these two, that's what you should be getting. All right, so those are all the t-tests that I'm going to cover. So you have a left tail, right tail, two-tail test. That's the extent to these problems. That's what you should be expecting. The next two tests that we have left are z-test and then your chi-squared test. So if I were to ask you, what are the keywords for a chi-squared test? What should come to your mind is variance. Variance is what is of importance now. Variance. So we're going to do chi-squared. So we will do chi-squared, and then we'll go to z-test. And again, you're going to have access to all this information. You're going to have a lot more practice problems. And if you have any questions, feel free to reach out to me. I am more than happy to help. Okay, so when we look at chi-square test, the null and the alternative, the parameter of interest is population variance. So population variance is equal to something. Population variance is greater than or less than something. So in this problem, and I'm going to highlight the problem for you, a machine produces bottles of soda with a claimed variance of 0.25 ounces squared. A sample of 20 bottles has a variance of 0.16 ounces squared. Test at the 0.05 significance level if the variance has less than claimed what was reported. So again, the keywords that jump out at you are variance. If you read through the problem, you'll notice that the alternative is asking if the variance is less than claimed. And what was claimed was 0.25 ounces. So it's going to be a left tail test for variance. So 0.25, making the null equal to 0.25. Now, I give you some important information here. Our n is going to be 20. Our sample variance is going to be 0.16. And alpha, in this case, is 0.05. Now, in order to do this problem, we need to find the test statistic. So the formula for that is n minus 1 sample variance divided by this. This comes from the null. This is given to you. This is also given to you. So if I plug everything in right now, so it's going to be 20 minus 1 multiplied by 0.16 divided by 0.25. If I find the statistic, or my evidence in this case, what I'm going to get is 12.16. This is my test stat. I need to compare this to a critical value. So my critical value for a left tail test is as such. So 1 minus alpha, comma, n minus 1. Because it's a left tail test, for a chi-square test, you can never have a negative critical value. The reason being, variance can never be negative. So the probabilities won't be negative, and this is what our distinction is. So it's going to be chi-squared 1 minus 0.05, comma, 20 minus 1. And if I look this up on my table, which you all have tables accessible to you, I would go to the column that has 1 minus 0.05, which is 0.95, and I would go all the way down to 19. And when you get that, you should get 10 point. You should get 10.1. So 10.1. So it's a left tail test still. So anything less than 10.1, we would say reject. Anything greater would be fail to reject. And you'll notice 12.116 is not in the shaded region. So we would say we fail to reject the null, conclude there's not enough evidence to support that the variance is less than 0.25 ounces squared. Something along those lines. So we fail to reject in this case because we're not in the rejection region. Now, if I were to ask you for a 95% confidence interval, 95% confidence interval, that is the next step of this problem. So the formulas for your LCO, it's the n minus 1 over s squared over the chi-squared critical value, in this case alpha divided by 2, comma n minus 1. And then our UCL is the n minus 1 s squared over the chi-squared 1 minus alpha divided by 2, comma n minus 1. So if I were to plug all these values in, what I'm going to end up getting is, for the LCL, it's going to be 0.09, and for the UCL, it's going to be 0.37. So the toughest part about this LCL and UCL is this right here, finding the critical values. So for the UCL, I'm sorry, for the LCL, you should get, let me just do the math real quick, 0.025, and you go down to 19, so you should get 32.9, and then 1 minus 0.025 would be 0.975. You should get 8.91. Now, if you don't get these exact values, do not worry. As long as you're in the ballpark, you're good to go. So again, steps. That's the biggest thing, is steps. So this is a left tail test. Left tail test with a confidence interval. If this was a right tail test, the only difference is the way you find your critical value. So the only difference would be the way you find your critical value. So if I were to switch this problem to greater than, we know we're looking at the right tail of the distribution. So anything greater than this critical value would be reject. Anything less than this value would be fail to reject. So we still know our chi-squared test statistic for this problem. That hasn't changed no matter what we do in terms of the sign. So in this case, it was 12.16. That's from what we just did. Now, the chi-squared critical value for a right tail test, so when it's greater than, is this. Alpha n minus 1. So I've already looked this up on my table. My alpha is 5%. If I go all the way down to n minus 1, which is 19, it is 30.1. That's what I'm looking at. So anything greater than 30.1, we would reject. In this case, 12.16 does not fall in the rejection region. So we still would say, fail to reject the null, not enough evidence to support that the variance is greater than 0.25. So again, very similar. The only difference is this portion for left and right tail test. All right, the next test is going to be a z-test. So z-test, the key word is proportions. When you see proportions, you know you are working with a z-test. So proportions or percentages, we're going to do some practice problems with that. All right, so for a z-test, I'm going to ask you for the p-value approach and the rejection region approach. So you should be able to do both. So for this example, we'll have our null and alternative. Because it's a z-test, the parameter of interest is going to be p, which is population proportion. So it can be greater than, less than, or not equal to some value. So we're going to start with the rejection region and then we're going to go to our p-value approach. So in this case, what we're going to have is a researcher claims that less than 30% of people prefer tea over coffee. In a survey of 400 people, 100 said they preferred tea. Test is claimed at the significance level of 0.05. So what we're trying to test is a researcher claims that less than 30% of people prefer tea over coffee. So what he's assuming is less than 0.30, or 30% of people prefer tea over coffee. So we're assuming the null is equal to 0.30. Again, same values, same symbols. Now I'll give you some important information. X is 100, N is 400, alpha in this case is 0.05. So the first thing for the rejection region is your z-stat. Find your formula. It's the p hat minus p over the square root of p 1 minus p over n. My p hat, the way I find my p hat is x over n. So 100 over 400. So you should get 0.25. So if I plug everything in, it's 0.25 minus 0.30. I get this from right here. Over 400. If I do all this, my z-stat, or my evidence, is going to be negative 2.18. So negative 2.18 is my z-stat. You should be getting something in this ballpark. If you're not, or if it's off by a couple, don't worry. The biggest thing is that you are on the right steps. All right, so that's our z-stat. Now our critical value, I've given you these before. So the critical value for 0.05, when it's a left tail test, has to be negative. So it's going to be negative 1.645. So if I were to draw this out, anything to the left of 1.645 that is negative is going to be reject. Anything not in the shaded region is fail to reject. So negative 2.18 falls in the rejection region. So my decision in this case is reject the null, conclude there's enough evidence to support that less than 30% of people prefer tea over coffee. All right, so this is the rejection region. The next step would be if I ask you for the p-value approach. This is something else that you can do and you're going to be expected to do, and it's just good to know because p-value is given with a lot of statistical programs, R, Python, Excel, Stata, eViews if you want to go that far back. So the p-value approach, it's the probability that p hat is going to be, in this case, less than, we still use the same symbol, less than whatever our p hat was calculated to be, which is 0.25. So we want to standardize this. So we have formulas to standardize. It's the probability that p hat minus p over the square root of p 1 minus p over n is less than 0.25 minus 0.30. You plug in all the other values. So this portion right here should reduce down to the letter z. So we're trying to find the probability that z is less than, and we already have calculated this entire thing. This was negative 2.18. So once you get it to this portion right here, you should be able to go to your z table, which I've given you. You go to negative 2.18, and the p-value is 0.0146, I believe. Yeah, 0.0416. I'll have students ask, well, what do I do with this p-value now? This is your p-value. You want to compare this to your alpha. So if your p-value is greater than alpha, we fail to reject. If p-value is less than alpha, we reject. So in this case, we have 0.0146. We compare that to our alpha, which is given to us in the problem. And we know that 0.0146 is less than 0.05. Another way of looking at it is 1 cent is less than 5 cents. Oh, you can't see this. So 0.0146 is less than 0.05. So we reject the null, conclude the same decision. So that's the main differences between the two. Now, if this was greater than, and we're doing the p-value approach, if this was greater than, and we're doing the p-value approach, I could just go in, change some of these the signs. If this was greater than, this would be the probability that z is greater than negative 2.18. Now, what you would need to do is the complement rule. So that's 1 minus the probability that z is less than negative 2.18. That reduces down to 1 minus 0.0146. And the value for that should be .9854. So this is your new p-value. Is this greater than or less than our alpha? In this case, 98 cents is greater than 5 cents. So our decision would be failed to reject. So depending on the sign, depending on alpha, and depending on your p-value, that helps you make a decision. So that's the most intense it gets. Z-test, t-test, and then your chi-square test. Those are the three that we covered in this video. We'll talk more about practice problems. We'll do more in the near future, but this should be enough to get you through this next couple of weeks. If you have questions, again, feel free to reach out to me. Thank you all for watching.